Welcome back. We are in chapter 4b, the Laplace transform, and in this section we are dealing with section 2 of chapter 4b, electric circuits ODE. Electric circuits can form ordinary differential equations. We are interested in the following types of devices: the resistors, the inductors, and the capacitors. We have a current that is varying with time passing through a resistor. The voltage drop across these two terminal points is given by the resistance value times the current at that instance. And therefore, of course, if you have this, then simply moving R to the other side, then the current at the instance is given by the voltage drop across the terminal point divided by the constant R, where R is the resistance value in ohms. So you'll see that actually in the voltage and the current are changed by the constant value R. Now, an inductor and a capacitor behave slightly differently. The voltage drop across the inductor is actually dependent on the derivative of the current. So the faster the current is changing, the more voltage will be dropped across these 2 points. So the equation describing the voltage drop across an inductor is typically using the alphabet L. Inductor is in Henry. Henry is the unit for inductance or inductor. So the voltage drop across the inductor is L times the derivative of the current. And now if you want to find the current, then you integrate on both sides. Then the current at the instance is 1 over L. Then you have this accumulation function from integral of minus infinity to t, b tau d tau. So this is the fundamental theorem of calculus, showing this equation over here. Right, the last one is the capacitor. The capacitor also behaves differently. The voltage across the capacitor is 1 over C, where C is in farad, and it accumulates from negative infinity to the current time. So the voltage at that current time is integrated from negative infinity to current time, the current that has passed through d tau. And if you want to find what is what is dv dt, then you differentiate both sides. So it will be it equals to c dv dt. So with these 3 expressions with these 6 expressions of voltage and current across the 3 devices, resistor, capacitor, and inductor, then we can actually form differential equations. Let's see them in the next slide. The first example we'll deal with is RL circuit. We have resistor here and we have inductor here across in a series. So series means one followed by another. Now we have a voltage source, so maybe you can think of it as in this particular case we have a AC source. That means the source it will change with time. It is a cosine wave, so it's an AC alternating current where it is going at this frequency omega. Right. So at time t, we'll close the circuit and we'll form a closed loop. And when we have a closed loop, a current will flow from this this battery or this AC source in through the resistor, passing through the inductor and come back again, and keep on going round and round. And by the Kirchhoff's voltage law on the right hand side, Kirchhoff's voltage law says that V1 is equals to V2 plus V3. Okay, or maybe what we can say is that voltage drop across the whole circuit is equals to 0. Now you can review the idea. You will see this polarity here. This is plus and minus, so the voltage is plus and minus the other side, and plus and minus the other side. Okay, so we're going to review Kirchhoff's voltage law, and it says that the sum of voltage drop across a loop is equals to 0. Alright, so let's form the voltage drop across L and R when the switch is closed. So this is IT, so the voltage drop plus and minus, or voltage drop across the resistor is I of T times R. The voltage drop across the inductor plus and minus is equals to L di dt. Why the plus here is because the current is going into the device first. So where the current is going into, we put a plus. Okay. By Kirchhoff's voltage law, we have Vs is equals to VR plus VL. So we have L di dt plus Ri. So this is the differential equations. Why differential equations? If you look at this carefully, once you have L, once you have R, these are constants. Whereas the differential equations, this is the ordinary part. We have only, with respect to T, we only have first order, in fact. And then on the right hand side, this is simply some constant, nothing not associated with I. And then we can solve for this first order ordinary linear differential equation. Okay, let's study a more complicated example. We can generate second order differential equations with RLC. So now we have again the circuit in series. So the word series means we put these what do you call it? These devices one after another. So it can be RLC, of course it can be LRC, it doesn't really matter. Now again, we in this particular case, the switch has been closed and the current is flowing across time. Alright, so we are going to we want to study the problem now, where the problem is we are given xt and we want to find the voltage across the capacitor. So that's our goal. Find yt. Yt is defined as the voltage across capacitor. Alright, let's write the Kirchhoff's voltage law first, which says that the voltages across the loop is equals to 0. So we just make sure we get the sign right, plus and minus, plus and minus, plus and minus. So we are saying that the voltage source, we put it at minus because actually if we want to, you can put it on the right hand side. Is this voltage drop across equals to xt. Anyway, so we have the voltage source, voltage drop across the resistor first, voltage drop across the inductor, which is L di dt, and yt. Alright, so now what we want to do is to we want to generate a differential equation with some yt, dyt, dt, and d2y dt. How do we do that? This is a trick. We want to actually change it into this. So if you refer to the equations here, it is equals to c dv dt. Alright, so we have this expression here. We're going to say the current across everybody is can be expressed as c dyt dt. dyt is the voltage drop across the capacitor, and it, whether it is here or here or here or here, is the same. Okay, so now we can now put it as c dyt dt. So this is it. So what about here? So the it dt, well, we differentiate it again, so we want to do dt, and therefore now we have c d2y dt. So the second order pops out. xt is the same, yt is the same, and now we have a second order differential equation. Second order because we have d2 here. Ordinary because we only have one independent variable. So this is the first order, this is the second order. The expression associated with all these derivatives are constant. I mean, the resistor don't change, the capacitor don't change, the inductor don't change. So these are constant. So it's constant coefficient, ordinary, second order differential equations. Okay, so it's very nice. We can see how we can have a very simple circuit like this to generate a second order differential equations for us to solve. So with that, in this course, we are only going to deal with series circuits. We're not deal with parallel circuits, and we're only going to deal with up to RLC circuits arranged this way. Right, thank you.